So that's what I'm doing here. All right, good. All right, so let's talk about this. So, so the lab is using something called dialysis tubing. And so dialysis tubing looks like this, and it is, it's dry right now. We use it when it's wet, but what it does is it comes in a roll like this, and I just cut off a smaller, it has two ends here. All right, a roll like this, and so I cut it off, and what it does is we use it for making artificial cells, and the reason why is because it has pores in it, and so they're microscopic, you can't see it, but there are these pores, and the pores have a certain size, and so what happens is we can make artificial cells out of them, because it's called dialysis tubing because it's a tube. So right now it's dry, it's not pliable, you have to wet it, but if you wet it and go like this at the end, it'll open up, and it's a tube all the way through, so they're open at both ends. And so what happens is when it's wet, you can make artificial cells. So this is what it looks like, and then you can take the end and tie it off using, we're just going to use sewing thread. And so what we do is that we just twist the end, tie it off, and I have you do double knots just to make sure that it's nice and tight. Usually that works pretty well. And then you can put solutions in here and tie off the other end and get a fake cell. And so what happens is then you can put it into water or another solution, and molecules can move back and forth, kind of like in a cell, moving back and forth into or out of the cell, based upon whether or not the molecules can fit through the pores in the membrane. So therefore, if the molecules are in here and they're small enough, they can move back and forth through the pores, but if they're too big, they don't. So therefore, the dialysis tubing is simulating a cell in the cell membrane by being selectively permeable, but unlike the cell membrane, this is only selectively permeable upon size. So the cell membrane is selectively permeable on size, as well as whether it's polarity and whether it's hydrophobic or polar and so on. So therefore, we're using this selectively permeable membrane. Now it tells you that each group you're going to have 3 setups and 3 solutions or 3 cells that you're going to make. What was in one of them? Sucrose, right? So it said a 1 molar sucrose solution. So what that's telling you is concentration. So in the examples we just went over, I used percentages as giving you information about concentration. Molarity is another concentration. So it's, remember, moles per liter. So to make a 1 molar sucrose solution, I get the molar mass of sucrose, which is 342, mass it out on a balance, put it into a flask, put some water in it, dissolve it, and bring it up to a liter. All right, and so that's the solution you're going to have available. I'll have them available. I haven't made them up yet, but I'll probably put like one up here and one right here. And because you're going to have a 1 molar sodium chloride solution, that's salt. And then you're going to have water, just pure water. What molarity is that? 0, there's no solutes, all right? So that's no solutes whatsoever in 100% pure water. So these are your 3 solutions. So you're gonna make 3 cells, each with those 3 solutions in each one of those. And so therefore, with the solution, I'm gonna have a 10 milliliter graduated cylinder, because that's how much it tells you to put in it. So you're gonna measure out 10 milliliters of the solution and put it in there. So the 10 milliliters, how you're going to put that in there is, because these tubes are hard to pour into, so I'm going to have funnels like this, and then you can pour your 10 milliliters in, and it'll go into your cell. And so it will not fill the whole dialysis tubing bag. So then what you're going to do is you're going to take your hand and squeeze out all the air. So you're going to squeeze it out, take off the funnel there, and then once you squeeze out all the air, you're going to tie off the end, all right, over here. So therefore, you're going to have a lot of space in here. Why do you suppose that I want you to do that? Because every year I have kids that want to tie it right here and make a little cell and have all this hanging off. But I want you to do it at the end. Go ahead. Alexis.
Oh, but the water will like absorb into the dialysis tubing. How would so you have space?
Yeah, so you have more space for the molecules to diffuse either into or out of the cell. So what that's doing is increasing the surface area, right? So your volume is your 10 milliliters, so you have that volume, but then if you have it, because once you go like this and go like this, it'll kind of go out throughout the cell, and so you have that 10 milliliters with lots of surface area for diffusion to occur. And so diffusion will occur, remember, if the molecules are smaller than the pores. All right, so then it tells you you're going to, once you make your cells, so you're going to have a beaker, and you're going to put the tube in the beaker, and it tells you you're going to immerse it into 200 milliliters of water. So that's the water on the outside. And so then it tells you to let it sit for how long?
30 minutes.
30 minutes. Maybe change that to 20. Change that to 20. Last year I found that that in our time constraints, by the time everybody got the three made and started timing, to get it all done, we had to reduce it to 20 minutes, and we still got good results. So 20 minutes is fine. So so you're making 3 of these first, and then putting it in here. So you're gonna have 3 setups kind of going on at once with the things that's varying is the contents of the cell. 1 molar sucrose, 1 molar sodium chloride, and water. And so how we're going to do this is in groups. So you're going to have 3 per group, and I'm just going to have tables work together. So you guys work together, you guys work together, you guys get the pattern. All right, back there, and then here, and then you guys only went to, let's see here. Griffin should be here, Sheldon. We'll play it by ear. We'll pull you in maybe. Okay, just like today we have a couple people left. Okay, so you'll set that up and let it sit for 30 minutes. But what were you supposed to do before we let it sit? Take the mass, right? And so I have 2 scales. Here I have 2 balances here, 1 right up here, and I put 1 on the back counter there. So you can just mass it, so you get your initial mass, and then we're going to get, after it's all done, your final mass, and therefore either the cell will either have gained mass or lost mass, and what that does is give you some information about which way molecules move, all right, whether or not the cell gained or lost mass, all right? So what I'm going to have us do now is, so that's the kind of the background of it, is if you're going to make some hypotheses. So look at this sheet here that says demonstration of dialysis tubing right here. And what I'm going to have you do, so notice it says set up illustration. So you're going to have 3 setups, an A, B, and C. So this is the A, B, and C that I wrote up here. Sucrose, sodium chloride, and water. And so when I say illustration, I'm looking for you to draw something like this. And what I'd like you to do is label what's inside the tubing or the cell, what's outside the tubing in terms of molecules. So for instance, a 1 molar sucrose solution, what molecules are in there? Sucrose and water, right? So it's not just sucrose in there. So it's a 1 molar sucrose plus water in there. And so you're going to label where the molecules are, and then I want you to draw an arrow if you think the molecules are going to move. When I say move, do you think that sucrose is going to move outside the cell? Do you think water is going to move outside the cell? Do you think water is going to move inside the cell? So therefore, you're going to, where you write the molecule here, like water, if you think water is going to go into the cell, you write water on the outside and then an arrow in that water is going to go in. And then underneath it, I want you to write that out. So I think this is what's going to happen, all right, in terms of the movement of molecules. So underneath it, write about the movement. of molecules, and then I want you to, the second part of what I want you to write underneath there is whether or not you think it's going to gain or lose or stay the same, the mass. All right, so you're making a hypothesis on that, and you're drawing in arrows up here. All right, and you're going to do that for all three of your setups. So you're making a hypothesis. You can talk amongst yourselves about what you think is going to happen. I want you to use a hypothesis is based upon prior knowledge, so things that you know. You should know from what we've done in class some things about sucrose and what it is, how its formula, how many atoms it's made up of, the size of it. Same thing with sodium chloride. Same thing with water. So I want you to think about that. Think about dialysis tubing, and it's selectively permeable based upon size, and therefore make some hypothesis from that. It is okay if you talk amongst yourselves and you disagree with other people. You can make your own hypothesis, and so they don't all have to be the same, like in the lab group. All right, so you can make your own hypotheses. And then after you make your hypothesis, underneath there it says construct a data table to record your information. So I actually want you to make a data table about the things that on Monday when we actually do this, the things that you are going to need to record. So you're going to make a data table here to record those things. One thing I want to point out before I set you loose on this is when we, I said when we get the mass at the end, it can either gain or lose mass or stay the same, and that tells you a little bit about what diffusion happened. One other thing that we're going to do that it talked about in there is figure out the percent change in mass. So if a dialysis tubing bag lost 1 gram, all right, that's one piece of information, but it's more telling if you compare that to how much it massed to begin with. Let me give you an analogy of people losing weight. So if you have 2 people that lost 10 pounds, all right, that means something different if person 1 weighed 400 pounds to begin with and person 2 weighed 100 pounds to begin with. So therefore 10 pounds, while they lost the same amount, the one that weighed 100 pounds lost a greater percentage of their total body weight than the one that weighed 400. The same thing is true for when the dialysis tubing gain or lose mass. You can record how much it gained or lost, but I want you to divide it and give the percent change in mass, so comparing it to the mass it originally came in at, and so therefore you're comparing percentages, and it tells you how to do that. You basically get the difference and divide it by the original mass, all right, to get the percent change. And so that you're going to ultimately calculate as well. So I want to point that out so that you can think about that in making your data table. Okay? So right now I'm going to have you do your hypotheses and the data table. So go right ahead. And you can talk amongst yourselves. Oh, salty snacks.
So, like for the concentration, I'm just confused if we're given one
Right.
You want to just write 0.
Yeah, you can. Yeah.